Hey y'all, welcome back to astronomy. I'm going to spend a short amount of time today talking about the distance standard that gets us pretty far out. In fact, some of these, depending on what kind of explosion we observe, can actually measure all the way out to the edge of the universe. So we'll have two standards that we need to talk about. One is basically type 1a supernova. That'll be today or this short video. And then the other one will be Hubble's law, which we'll spend several days talking about just because it's so cool. And it leads off into a branch of astronomy, which we call cosmology, the study of the evolution of the universe. Okay? So let's get at it. So supernova, we've already discussed in the videos about the birth, life, and death of stars. Supernova occur for high mass stars, somewhere between, well, it depends, but could be as much as 4 to 7 solar masses. That's the general typical supernova. So supernova, we actually have 4 different groups of them. And I'm just going to give you the 4 different groups and show you some spectra just to give you a sense of how these distinguishing features are made. And then there's one in particular, the type 1a supernova, that we need to actually focus on. Okay? So there's 4 groups. The most important group in my mind is the type 1a's. So the first one is called a type 2, and it's a supernova that demonstrates hydrogen emission lines. I refer to this as a clothed giant. In other words, it has all of its outer layers still intact. So you think of this high mass star, this gobstopper, this onion, if you prefer that analogy. So it has all these layers. And the issue is that that outer layer of hydrogen is still intact. It hasn't been blown off into space for whatever reason. So if you see a hydrogen emission line, that is automatically a type 2 supernova. Here's an example of the spectra. Now let me walk you through this for a moment. So on the vertical axis, you have the magnitude of the lines, or the intensity. Horizontal axis is still the wavelength. Now what you see here is I have multiple lines drawn. The reason for that is that when an explosion occurs, it depends on when you look at it. So if you look at it right at the beginning, it might have one intensity. But as time progresses, the intensity will slowly fade. That's because that explosion is spreading out into space and therefore is going to be dimmer as time progresses. So each of these lines represents a different time point. I believe 13 days, 16 days, 17, 19, 15, 100, 119. So as you look at the lines going down, these are days after the initial explosion. Okay. Now you notice right here, I have the hydrogen alpha line marked, and you can see this emission. That means that hydrogen was present, that outer layer was still intact when the explosion occurred. So this would automatically be a type 2 supernova. Now I have a flow chart here. So if it has a hydrogen emission, yes, it's a type 2, otherwise no. Now the next 3 supernova are called type 1a, 1b, and 1c. And as you would probably suspect, initially it was just thought that these were all the same types of supernova. It wasn't until later that we realized that what was called a type 1 supernova actually had 3 different categories to it. So we kept the type 1 and we simply appended to it A, B, or C to distinguish between the 3. So the next step is that if it does not have a hydrogen emission line, okay? And the next question is, does it have a silicon absorption line? And this is very special. Okay? This is what we call a type 1a. And this is the one star that does not usually have enough mass to undergo a supernova. It's a white dwarf binary. Now remember, how do we get a white dwarf star in the first place? You have a medium mass star somewhere between 0.4 solar masses and 4 solar masses. Okay? So you have this medium mass star. It goes through its main sequence. It goes through its giant phase. It does all of these helium flashes and it ejects material out into space. Okay? This is the future fate of our sun. Okay? Now, after it ejects all of that material in space and the fusion reaction stops, you are left with a white dwarf, a star that is generally comprised of carbon. Follow me so far? Now, usually that star is inert. It will not do anything. It'll just sit in space and slowly cool off. Okay? This is the type of star that is involved in a type 1a supernova. It's particularly important that I mentioned not only is it a white dwarf, that's the star, but it has to be in a binary system. We'll talk about that in the next slide. Okay. Now, if it doesn't have a silicon absorption line, okay, so no for the helium emission line, helium emission, no for the hydrogen emission line, no for the silicon absorption line, then you lastly look at the helium absorption. If it has helium absorption, that means that the outer layer, the hydrogen layer, has been stripped off, but the helium layer is still there, that helium shell. Okay. If the helium shell has also been stripped off, then that's what we refer to as a type 1c. If the helium layer is still there, a type 1b. Okay. So I call a type 1b a strip giant. You remove the first layer. And a type 1c is like a naked giant. Okay, or a mugged giant. You've removed 2 layers of clothing, if you will. This is why I said I think I would have preferred type 2a, type 2b, type 2c, because those 3 are more closely related to one another. History is a bugger. Let's go back to this white dwarf binary. We've already talked about, hey, wait a minute, it's got to be a medium mass star that has burned out. And the silicon absorption, you see it's right here. What this indicates is that you had a carbon white dwarf, and remember, how do you form silicon? You have carbon-carbon fusion. Okay. So medium mass star has died out. It is this carbon white dwarf. And the question then becomes, how can this star restart? That's the key. How can it restart? How can it all of a sudden start doing carbon-carbon fusion? You have a white dwarf. Say it's sitting there, but it has a friend. It has a neighbor. It has a neighbor that's willing and close enough to give it some material. The binary star contributes additional material to the white dwarf that has been burned out. So this material falls to the white dwarf. It gets incorporated, and that white dwarf grows a little bit. Now, of course, this process is what we call accretion. It will grow, gradually increase its mass by stealing material from its companion star, its neighbor. We've actually seen this before. What you have down here is a photograph of a binary star system. And pictured is the white dwarf and a cloud of gas kind of surrounding the white dwarf, or in the neighborhood of the white dwarf. What is going on is this X in the middle is a second star, and this white dwarf is running, orbiting the star, and pulling material from the star. Okay. So it's gradually increasing in mass. Now remember, we have a white dwarf because it wasn't massive enough to start the carbon-carbon fusion process. But in this very rare instance, it's slowly growing in material, slowly snitching more and more mass. And what happens, and you can imagine, what happens if it accumulates enough material that all of a sudden the fusion process can start again? Almost like a helium flash, but now I'll call it a carbon flash. Okay? The carbon fusion isn't going on. This white dwarf slowly accumulates, accretes more and more material, and then you have a carbon flash. Boom! What happens? You get the sudden restart of the fusion process. That carbon-carbon fusion forms silicon. which is why we look for the silicon absorption line, and it's a huge explosion. That is what we call a type 1a supernova. Let me give you an HR diagram. Okay? And this is a different HR diagram. It looks kind of funky. Okay? So over here we have our standard HR diagram. And here it's in temperature, luminosity. The main sequence is highlighted right here. You have our red giant branch right here. The horizontal branch would be somewhere up here in your white dwarfs. Now these carbon white dwarfs, these medium mass stars that have burned out, okay, they're sitting right here. But if they accrete enough material and they go through this supernova process, it takes about 10 seconds to go from this location on the HR diagram up to 14 billion Kelvin. They go from 50,000 Kelvin to 14 billion Kelvin in 10 seconds. Roughly 10 seconds. And incidentally, they go from something like 10 to the negative fourth solar luminosities up to 10 to the sixth. Right? That's a 10 billion, that's a factor of 10 billion in about 10 seconds. So you go from 50,000 to 14 billion Kelvin. Excuse me, I said 14 billion, 14 million with an M. Kelvin, and you increase by a factor of 10 billion in luminosity in about 10 seconds. That's how big this explosion is. Boom. And in fact, you can get up after about a day, you can get up to 10 to the 10th, okay, in terms of luminosity. That's about the peak luminosity. If you're doing absolute magnitude, that's about negative 19.3. That's how luminous these stars become in the supernova process. Okay? Why is this so important? Why do I bother talking about this? Let's go ahead and take a look. Okay. There's something very special about these type 1a supernova. Okay. What you see before you here is a bunch of different supernova. Each colored dot represents the magnitude of the supernova and days either prior to or after the explosion. And go ahead, take a minute here. What do you notice about this? You notice that the light curve, notice I'm plotting luminosity versus time, or absolute magnitude versus time. So this is a light curve. You should notice that despite the fact that I have a whole bunch of different supernova, right? Each colored dot represents a different supernova. You notice that they all have the same light curve. Wait, why? Why would every single type 1a supernova have the same light curve? Imagine for a moment, it's the 4th of July. Okay? Now, I'm not a big firework fan. That's just not me, but I know a lot of people are. So imagine this for a second. You open up your pack of fireworks, your firecrackers, and you have a whole string of them, and you pull two of them apart. Okay? So you've got two firecrackers here from the same bag. And the question I have for you is this. If you light one of those firecrackers and it explodes, you see some brightness. You can perceive that. If you take the second firecracker and you light it and it explodes, how does the brightness of that firecracker, the second one, compare to the first? It's the same, or at least approximately. What I would argue is that you're using this idea. You're using the homogeneity of the firecrackers. The firecrackers are made out of the same stuff, they're the same size, they're the same material. Therefore, you would expect that when they explode, they roughly explode in the same way. Same brightness, same time, everything. We're doing the same thing, it's just that with this white dwarf. They're 1.4 solar mass white dwarfs, size, comprised of carbon, composition. So when they explode, we expect to get the same explosion. So that's why we notice that all supernova type 1As have the same light curve. They have the same peak brightness. This is what we refer to as a standard candle. We know roughly how bright they are. Every single type 1A explosion has an absolute magnitude of negative 19.3. The peak brightness of a type 1A explosion is something like negative 19.3. If you see a supernova explosion, you know that its peak brightness is 19.3. And in fact, it's even more helpful. Let me pull this up for a second. The shape of the light curve is always the same. So you don't actually have to see it when it's at peak brightness. You can look at it afterwards and still get an idea about it. Let me give you an example. Here is a light curve fitter. You'll use this in lab at some point. And I've selected a supernova, 1993J. Unfortunately, and you notice, we don't have a lot of data points for observations. Okay? But what we do know is that it was a type 1A supernova. And so it will have this shape of light curve. So we don't have to observe it at its peak. We can actually, and this is the cool thing about this, you can click and drag. If we can kind of get those data points, there we go, to fall on the light curve, now we have an idea, even though we didn't observe it, we have an idea about when it actually exploded. We can get an idea about its apparent magnitude and its absolute magnitude in this case. It's pretty cool. In fact, I'll put that in there. Notice that its peak brightness, oh, excuse me, I said 19.3. It should be negative 19.6. Okay. So that's the general byline, is that if you see the explosion, you can get an idea about its peak brightness. Okay. If you see a type 1A. So you have to see, does it have a silicon absorption line? Yes. Okay, then it was a type 1A explosion. And because it's a type 1A explosion, it will have this nice shape. And because it has this nice shape, we can estimate how bright it should be. Or I shouldn't say estimate, we know how bright it should be. And once we have the absolute magnitude, once we know how bright it should be, and we have the apparent magnitude, how bright it appears from Earth, we can now find the distance again. That you will do in lab with that explorer that I showed you. Okay. So where does this leave us? This, depending on how bright the explosion is and how good our cameras are, this will actually take us roughly to the edge of the universe, which is really neat. Okay. And we're going to use a second idea there to start talking about Hubble's law. So that's the short video that we have right now. Okay. It'll stretch us all the way out to something like 3 billion parsecs. That's all I have for you right now. I'm going to leave it there, just a brief video, but we'll pick up with Hubble's law next. Thanks for your attention. I'll see you soon.